magnetic environment in NMR. So this magnetic environment will definitely give the number of peaks or signals on the NMR spectra. So let's say we have this compound. Let's say we have this methanol again. So let's say that the number of hydrogen type is 2. So the peak on the spectra is going to be, we're going to have 2 different types. One here, maybe this way, or another one, maybe this way. Just an example. So basically, we're going to see 2 peaks. So the number or the types of hydrogen determines the number of peaks we are going to see on the spectra. So to identify the different types of protons or the different type of hydrogen in a given organic compound, you can always use these mnemonics. So we have BAS. So the first thing is bonded atom. So what atom is the proton directly bonded to? So looking at this here, in this case, the proton is bonded to carbon. The proton here is bonded to carbon. The proton here is bonded to carbon. But here, the proton is bonded to oxygen. So you may want to ask, is it bonded to carbon? Is it bonded to oxygen, nitrogen, sulfur, etc.? So the next thing you may want to ask is adjacent groups, right? So looking at this, okay, let's start with this bonded atom. So this one is bonded to oxygen, but these 3 are bonded to carbon. So definitely this hydrogen here is different from the hydrogens here, right? So let's call this 1. So we don't know if there is also another way we can differentiate this, but let's continue. Adjacent group. So what group is the proton indirectly bonded to? So the proton here is bonded to carbon and is indirectly bonded to OH group. The proton here is bonded to carbon and is also indirectly bonded to OH group. The proton here is bonded to carbon and still also indirectly bonded to OH group. So still the same thing for them all here. So is there symmetry in this structure? Of course none. There's no symmetry. So all these hydrogens here will be considered to be the same, right? So we have 2 types of hydrogen or 2 magnetic environments in this compound. So let's see some of these examples. So we've done this. So let's look at this CH3 or CH3. So you can also expand the structure as hydrogen, 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 oxygen, and we have hydrogen, hydrogen, hydrogen. So let's bring out back our BAS. So the bonded atom. So this one is bonded to carbon. This one is bonded to hydrogen and to carbon rather. This one is also bonded to carbon. This one is bonded to carbon, right? So now let's look at the next one, adjacent group. They are also bonded to the same adjacent group. Now all these are the same. All the carbons, all the hydrogens here, or all the protons here are the same. So now let's look at this also. Still the same thing. They are all bonded to the same atom and to the same group. So they are also the same. Now let's look at the third one, symmetry. Is there a symmetry here? Yeah, there's a symmetry here. So these carbons, we consider them as 1 initially. We consider this one as the same also. We said this one is A, this one is B. But now when we look at symmetry, these 2 sides are the same in symmetry. What is here is also what is here. So basically we can call this, it has just one magnetic environment. So we only have one type of proton here. It's just 1. So now let's look at this also. So this structure, let's draw the structure. We have this H3, H3. We have this hydrogen, hydrogen, and we have this hydrogen, hydrogen, and hydrogen. So now this is bonded, looking at BAS again, it's bonded to carbon, bonded to carbon, bonded to carbon. This one is bonded to carbon, bonded to carbon, bonded to carbon. This one is also bonded to carbon. But let's look at the adjacent group. This one is bonded to 2 carbon, one here, one here. So this one is definitely different. The proton here are different, right? These 2 protons are the same, but they are different from these 2. So the carbon here is bonded, the proton here is bonded to a carbon that is bonded to a carbon. It's bonded to a carbon that is bonded to carbon. So let's say that this one are the same also with this, right? Now let's confirm. So there's symmetry there. Is there symmetry? Yeah, there's a symmetry here. What is here is also what is here. So we have two, just this one is considered to be 1 and this is 2. So we have just 2 magnetic environment or 2 types of protons there. So now let's look at this structure, hydroxyl cyclopentane. So this is cyclopentane and we have hydroxyl there. So this is hydroxyl cyclopentane, but let's draw it out in a better way. So we have this one to be OH. So we have this to be CH2. We have this to be CH2. We have this to be CH2. And we have this to be CH2. So each one of them has 4 bonds. Each of the carbon has 4 bonds. 1, 2, 3, 4. 2, 3, 4. 2, 3, 4. 2, 3, 4. So let's look at this 1, 2, 3. So there's hydrogen here. So in all of these places there are hydrogens, right? So now let's look at this, the bonded atom. So this one is bonded to oxygen. So we'll call this 1. So these ones are bonded to carbon, bonded to carbon, bonded to carbon, bonded to carbon. But this one are H2, 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 H2. And this one is just 1. So this one is also different. We have it to be B. So now let's look at these ones. So these ones are like the same thing, the same thing. And now let's check the adjacent atoms. So it's also connected to the same this. The proton here is connected to a carbon that's also connected to this. Same also this one. So we can say that these two are the same. They are the same. We are going to call them C. They are the same. We are calling them C. And this also, they are the same. We are calling them D. And they are different from this one. This one is joined to a carbon that is joined to OH. But this one is joined to a carbon that is joined to another carbon. So they are different. So basically we have 1, 2, 3, 4. We have 4 magnetic environments. Let's also look at this benzene. So this is structure of benzene, which is also the same thing as this. So we have this to be just hydrogen, 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 and hydrogen. So we can put the double bond there. So let's look at this. So BAS is bonded, the bonded atom is bonded to carbon, bonded to carbon, carbon. Everything is bonded to carbon. Now adjacent atom, this one is bonded to carbon, that is bonded to another carbon. So the double bond is bonded to carbon, that is bonded to another carbon. And recall that this double bond is the same thing as this, like is in resonance, right? So what we can say here is that everything here is just one type of proton, one magnetic environment. So let's look at this one. We have it to be, this is a structure, and we have it to be OH. So also let's open it out. We have this to be this OH. We have C H2, C H2. We have CH2, we have CH2, and we have this to be C H2 as well. So all of these, this is a proton, right? So this is, there's also an hydrogen here. So we have this to be B, another proton. So now these two protons are the same. these two protons are also the same, and this one is different. So we have this to be C, D, and E. So we have 5 magnetic environments. So now let's look at this 2,2-dimethyl propane. So propane is CH3, CH3, and we have 2,2-dimethyl. So that's going to be CH3, CH3, right? So how many magnetic environments? So basically it's going to be one magnetic environment. All of them are same, so it's going to be one magnetic environment. Let's look at pentane, CH3, CH2, 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 and then CH3. So this one is the same as this one here. There's symmetry at the middle here, basically the symmetry. So this is a proton, and this is another proton. Like this one are the same. This is another proton also. So we have 3 magnetic environments. So now let's look at these last 2 questions. So we have this. So basically all of these are the same. The protons here are the same, just 1, and the one here is also 1. So we have 2 magnetic environments here. So looking at this also, so benzene, so we have a structure here. So we have it to be this. Let's draw it. 1 bromo, let's call this bromo. So 2 methyl, let's call this CH3. Benzene, this is 1. So now looking at this one, we can draw it again to be this Br, and we have this to be C, have this to be C, then to CH3. So we have this to be C, hydrogen, we have this to be C, hydrogen, C, and this to be hydrogen as well. So this is 1, 2, C. This is, let's put it CH2. Let's put this one also CH2. This one is 1, 2, 3. So this is CH. So this also is CH2, right? And this is CH. So there's proton here, call this 1. There's also a proton here that is different from this. So we'll call this B. So we're going to call this C. Like the proton here is C. So this one here is basically different from this. So this is D. Also this one is different. This one is E. This one is different, F, and then G. So that's 1, 2, 3, 4, 5, 6, 7. So we have 7 magnetic environments for this. So now let's look at the area of peak and the integral value. So this simply gives the number of hydrogen in that peak. So let's say this is the NMR spectra, and let's say we have a peak here. Let's say we have another peak here. Let's say we have another peak here, right? So basically, the area of peaks or integral value, this simply gives the number of hydrogen in that peak. So this in most cases will be given to us in form of integral values like this, like a ratio. But in reality, the machine now has an integrator that computes this value. So let's say the integrator are given to be this 2:3:3. So this means that there are 2 hydrogens here, there are 3 hydrogens here, and there are 3 hydrogens here. So 2 hydrogen ratio of 3 hydrogen ratio of 3 hydrogen. So when you see such values, it's simply telling you the number of hydrogens in that peak. Now let's quickly look at the spin-spin splitting. So recall that we said that a proton in NMR spectrometer has both external magnetic field and the induced field of the shielding electrons. So if there are other protons nearby, so let's say we have this structure, let's say we have this, we have this. So let's call this let's say this is joined to OH. This is 2 and this is 3, right? So if there are other protons, so we have 3 types of protons here. We have the 1, which are these 3, we have the 2, and we have the 3. So if there are other protons nearby, their small magnetic field also affect the absorption spectra of the protons we are observing. So let's say we are observing this, the magnetic field of this would also affect this, and the magnetic field of this will also affect this. So as a result of this, many signals do not appear as a single peak. So because of this particular reason, splitting, we do not have single split for some spectra. So if you are to see this spectra, because we have 2 here, so let's say, assuming it was initially thought that all spectra should be single, right? Should be single spectra. But now introducing this concept, spin splitting. So this this one affects this one affects this also. So it has to be adjacent. Since this one is not adjacent, it's not going to have any effect, right? That is adjacent in the sense that the only distance between them is this, like this proton that is joined to a carbon and is now connected to another carbon that has a proton, unlike this one that has oxygen. No. So now the effect is that if this was to be the peak of the CH3 here, and let's call this A, and this one let's call this B, and this one C, right? So B and C. So since this one is CH3, the first one is CH3 and the second one is CH2, right? So 3 proton A will split this one. So we are now going to have 4 peak. So it's going to be, the middle one is going to be 4, like this, 4 peaks, right? Basically, look at it. This one is the 3 hydrogens, right? This one is the 2 hydrogen. So this one is splitting this one is splitting this one. So this one we're going to be like 1 plus 3. I will give you 4 peaks. So for this, it's going to be 3. It's going to be 3 plus. For this one, it's going to be 2 plus 1 peak. Like 2 things are splitting. Okay, let's say this is the single split, right? This is the single peak. So 2 things comes here. So we are going to have this 2 and then 3. So for the 4, for this this one, when this one was splitting the single peak, it's going to be 3, 1, 2, 3. So we are going to have 1, 2, 3, 4. That was why we have 4 here. So for this is going to be 3. So it's going to be this, this, and this. And there's a way these are drawn according to there's a way it's actually drawn. There's a rule it follows. The first peak is going to be, if it's a single peak, 1. If it's 2 peak, they have the same size. If it's 3 peak, it's going to be this, according to Pascal stuff. So it's going to be something like this. If it's 4, it's going to be this. The middle 2 will be of equal size, almost of equal size. If it's 5, it's going to be this. So the third will be higher. So it's going to be this. So these are this. So the OH here does not partake in this splitting because it's not adjacent to these two. It's when we have something like this that the splitting occurs. Not even on the same carbon, no. So the condition, it occurs when the 2 types of protons are close enough that they are adjacent. It is reciprocal. One split the other. If one splits another, the second must also split the first. So it occurs only between adjacent protons. So it occurs between these protons and not even between these, right? So let's take a look at coupling effect as well. So coupling effect in benzene, we're just going to talk about the benzene. All these values will be given to you in your question, particularly when it has to do with matching spectral values. So looking at this, so when it is auto like this, the proton and this, so the J coupling effect is going to be between 6 to 9 hertz. So the J value will be this. So when this is auto, so when it is meta, it's going to be this. That's going to be hydrogen and hydrogen. So it's going to be between 1 to 4 hertz. So when it is para, it's going to be between let's look at it. It's going to be between 0 to 0.9 hertz. So these are the J values for this. So now let's see the next thing. So the next thing is chemical shift value. So this, in many textbooks, they will always give you a value, overlapping values. Like they will give values and then they give overlapping values. This one to this, this one to this, this one to this. So these values can be very, very confusing. But I'm just going to give you these definite values, but they are not always fixed. So I'll also tell you when they are not fixed, but try to know this. It's the most foundational to whatever you'll be doing in this topic NMR. So the first thing is that a proton like this, when we have CH3, like in the case of let's say we have, in the case of this, in the case here, the CH3 here, okay, 1, 2, 3, okay, CH3 basically, CH3 should be around 0.9. Please take note of that. It will be around 0.9. The table is always between 0 to 10, but can be extended to like 14 depending on the type. So sometimes you might even see it's up to 12, but depending on the type. So CH3 is 0.9, right? So when we have CH2, it is around 1.3. So it is around 1.3. But it's important to note these values can also change. I will tell you when they can change. They can change in the presence of electronegative values, but I will tell you. Let's continue. So we can also have CH value. CH value is around 1.4, right? So now we can also have the proton, this kind of proton. So this proton here is like, this one is always, in many cases, always 2.1. So take note of this 2.1. The proton on this CH3 here that is joined to C double bond O. So let's look at this also in alkyne. So the proton here is basically 2.5. It's around 2.5. So another one is this. Now when you have CH2 joined to electronegative atom or halogens, where X equals to halogens or oxygen, so the value is around 3 to 4. Please take note of this. It's around 3 to 4. So another one is this, when you have this alkene. So the hydrogen in alkene, is around 5 to 6, right? So another one is this. We have alkane, but then you are now having CH3. Hydrogen has joined to carbon before joining to this. So this would be 1.7, around 1.7. So please take note of that. So now when we have benzene, let's say we have benzene, this is benzene ring having all hydrogen. Let's say it's hydrogen, 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 hydrogen. So this is usually around 7.2. The hydrogens here, that is the protons here, are usually around 7.2. So let's say we have again, let's say we have benzene, let's put hydrogen, 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 and now let's say we have this one, CH3. All these are still around 7.2, 7.5 or so, but this one here is going to be around 2.3, right? Around 2.3. So aldehyde, like in the case of CHO, the aldehyde is usually between 9 to 10, and carboxylic, the proton in acid, in this kind of acid, is usually between 10 to 12, right? So this one is between 3 to 4. Now it's important to note a numeric proton rider. A numeric proton like OH, SH, NH, they usually have a value between 4.5 to 5.0. So it's important that you know all these values, 4.5 to 5.0 there. So the effect of an electronegative group on the chemical shift can depend on distance. So let's say we have CH3. In the case of methanol, let's say CH3, CH2, and oxygen, right? So this is OH. So recall that we said this was supposed to be 0.9, right? We said it was supposed to be 0.9, and we said this was supposed to be 1.3. But because there is an electronegative atom around, it's going to like de-shield them. So this one is going to be around 4.5 to 5.0, whichever value. 4.5, you can give it 4.6. But looking at this is already close to something similar to this. So it's going to de-shield it from 1.3 to around 3, we can call it 3.4. And for this one was 0.1 initially. So will this oxygen here, will it affect the protons here? For you to answer that, you need to draw it this way to check the number of bonds. If the bond is beyond 3, then the oxygen will not have an effect. But if it's still within 3, it will have an effect. So we have this, so we have C, H, H, and we have OH, right? So now this one is basically, this is the oxygen here. So let's count the number of bonds. 1, 2, 3. So for each of them is 3. So this will have an effect. The electronegative atom will have an effect on their value. So their value can actually rise to like 1.1 or 1.2 or even 1.0. It's still greater than this. So that is that. So we've seen ammonia, methanol. So now let's look at 1-bromobutane. So 1-bromobutane is CH3, CH2, 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 Br, which is also the same thing as, let's draw it out, hydrogen, hydrogen, hydrogen. We have this, we have this, we have this, and we have bromine here. So now looking at this, how many magnetic environments do we have? This is 1, we call it A. This is 2, we call it B. We call it this C. and we'll call this D. So we have 4 magnetic environments. All of them are different from each other. So now let's look at this. Let's suggest some NMR, proton NMR values for this. So we said that CH2 as bonded to X halogens should be around 3 to 4. So definitely this is going to be around like 3.4 or 3.5, whatever. So this is CH2, right? And CH2 is basically around 1.3. So CH2 is basically around 1.3. So but the presence of this will be felt by this. We have 1, 2, 3. So it's going to be 1. We can call it 1.5, right? So looking at this one is CH2. So it's meant to be 1.3 also. But let's see, would there be an effect? 1, 2, 3, 4. So no effect, is going to be 1.3, and this one is going to be 0.9. No effect. So that is that. So this is going to be for us to predict the chemical shift of the protons in the following compound. So recall that we said this CH3, the protons in this has a value of 2.1, right, ppm. So this here we have 2 magnetic environment or 2 proton types. So this is going to be 2.1, and this is definitely going to be a numeric proton, right? So that's going to be between 4 to 5, and we're going to give it a value. Let's call it 4.7. Yeah. So for this as well, how many protons do we have? We have a proton A, another proton A, and another proton A. So this is similar to CH2X, where X is halogen or oxygen, and this will definitely going to give a value between 3 to 4. So let's give this 3.7. So this is still joined with 1, 2, 3. So this will give us a shielded a deshielded effect as well, because it's still within the 3 bond limit. So this, instead of 1.3, this is going to give us around 1.6 or 1.7. So but this is far away already. CH3 here, let's count 1, 2, 3, 4. So this is going to give us 0.9. So looking at this also, we have the C double bond CH2. So we have this to be hydrogen. We can call this C, and then we have CH3, CH3, CH3. So now let's look at the magnetic environment. There's one here, there's another here. So all these 3, remember the BAS, all these 3 are joined to the same atom that are connected to the same group. So we have all this to be C. So this is going to be this is alkene. So this will give us, the proton here will be around 5.7 maybe, or between 5 to 6. So this one here will be greater than this. So this will probably give around 5.9. So the protons here are far away from the double bond, or let's confirm 1, 2, 3. Okay, they are still within. So this may give around 1.1. All the protons here will give around 1.1 or 1.2. So now let's talk about the multiplicity. So multiplicity is basically m equals to n plus 1, where n is the number of neighboring hydrogens. Alright, so looking at this question, predict the structure of the compound with the following proton NMR data. So for you to answer this, the first thing you need to do is to calculate the double bond equivalence. So it's calculated using this formula: Hn 2n plus 2, and we have this to be this. So the equation is this. So it's going to be n equals to 4, right? So we're going to have C4 H8 plus 2. That will give C4 H10. So now let's see C4 H8 C4 H10. So that's basically going to remain H2. So that will be n equals to 2 over 2. Assuming it was 4, it's going to be 4 over 2. So this will give us one double bond equivalence, which is the same thing as one double bond equivalence, or okay, let's leave it there. So we're going to have one double bond equivalence. So most likely there's a kind of double bond somewhere, right? So we have this to be C4 and this, and let's look at the spectral value. We have this, these are the spectral value. So these are the integral value, number of hydrogens. We can say we have 2 hydrogens, let's say for now, or let's put it this way: 2 hydrogens, 3 hydrogens, and 3 hydrogens. So looking at this, the first thing we need to do, we can identify this naturally from the chemical shift table to be this, right? Another thing we can also do is to, we can also just obtain the value from, just obtain the structure from the value given here. So looking at this one says that it has this one is for these 2, this one here is for these 3, and the last one here is for these 3. So it's saying that this one has 2 hydrogen, and since it's coated means 4 equals to n plus 1, so it has 3 neighbors, right? So 2 hydrogens having 3 neighbors, right? So let's look at this also. So this one is 3 hydrogens, right? 3 hydrogens having, this one singlet having 0 neighbors, right? And the last one is triplet. So 2 is 3 hydrogen as well, as having 2 neighbors. No, this is T, this is 3. That's 3 equals to n plus 1, and that will give us n equals to 2. So 3 hydrogen is going to give having how many neighbors? Having 2 neighbors. So this one tally with each other: 2 hydrogen having 3 neighbors, 3 hydrogen having 2 neighbors. So we can therefore say that this is going to be CH3 CH2, right? Now we need to know this one. We need to know this last one. That's 0 neighbors, right? So I will be able to like account for 2. Now we need to account for 2 more carbons, and then what else again? We have 5 hydrogens. We have this to be 8. So we need to account for 3 hydrogens and 1 oxygen. So if you look at this carefully, we have 2 carbons, right, to account for this, 3 hydrogen and this. So we can therefore see that this is a structure, right? CH3. So you can assign the values there again, which is 2.1 singlet. This one is 2.4 quartet, and this one is 1.1 triplet. So that is that.